们开始了，我们继续来自 Soochow University 的唐景惠老师继续跟我们讲这个 p-adic 群的表示了话题。
谢谢。So yesterday we defined parabolic induction, and in particular is induction of representation. And if you recall, in finite groups, we have this Frobenius reciprocity, which is very important in, representation theory, and also for category, this is important identity. So we call, okay, let me write down the situation for finite groups. So for finite groups, for this G, if it is finite, then say we have, say if I have, maybe I should involve two groups, G and H. H is a subgroup of G. And pi is a representation of G. And sigma is a representation of H. We have four. So the intertwining space pi and the induced representation from H to G of sigma. Okay, so this is a representation of P. Okay, and also for pi, and you compare this all the linear homomorphisms from pi to this induced representation, which is all intertwined by all G. Okay, so this is the intertwining space. This is isomorphic to the H intertwining space of. Okay, so here I bring down my induced representation sigma, but here we have restricted representation. Okay, so it's just viewing pi as a representation of H. Okay, so this is quite familiar. But now if I want to use it in the p-adic case, then you'll see some problems. Okay, so let me, I usually consider H to be a parabolic subgroup, so let me write it in this way, from P to G. Okay, so say you want this. Well, actually this is still true, but okay, this is still true. But actually this side is a bit problematic. Okay. For example, this P is not. Okay. Then, this is not a very good group, because for reductive group we have a good theory for maybe put it this way. For reductive group we have a good classification of representation. But if P is not reductive, then there could be some problems. Okay, so this is one thing. Second is, okay, even though, okay, say remember this sigma originally is a representation of M. Okay, this M is the Levy component of P. Remember this P is N times N. Okay, originally sigma is a representation of M, but I extend trivially to N to form this representation for P. Now, even though you restrict to M, okay, even though, what should I say? Okay, even if we further restrict to M, okay, so you want to consider this representation. But this is in general not admissible, even though pi is admissible. Okay? Because you can see, if you want to check the admissibility, you want to check something like this. You want a compact subgroup in M. Right? If you want to view it, okay, maybe write it in this way. You view it as a representation of M. If you want to check admissibility, then you take complex subgroups in M, and you check the dimension. Okay? This restriction is just your original pi. If you compare this dimension to this, even though this is finite, but this could be infinite. Okay, because this M intersect K is much smaller than K. Can you see that? Yeah. So these are the problems. Maybe there are more problems. So here I'll give you one construction. So this is due to Jacquet. We call it Jacquet restriction, or sometimes we call it Jacquet module. Okay, so I'll give you the construction so that we will have a nice result here. Okay, reciprocity result. So say if I have a smooth representation of G, okay. Again, G is a reductive p-adic. Okay, I won't write it down again. Okay, so G is a reductive p-adic group. Now define. Well, say I should fix a parabolic subgroup. Say standard. Okay. Well, you can imagine this is standard, but it doesn't really matter. Okay, so I fix a parabolic subgroup. Then I define the following. I define V bracket N to be the span of all such vectors. So I let an element in N acting on a vector V and subtract the vector itself. Okay, so and I let N in N and V in V. Okay, so I span all such vectors, and then I define V sub N to be V, my original representation, dividing this subspace. Okay, so what am I doing? Remember, in parabolic induction, I extend a representation trivially to N. Okay, it's an artificial process. Now, for the restriction, I do something well similar, but it's like a dual process. Okay, I artificially mod out all these vectors. You see, if I quotient out this Vn, then any n action on this quotient maps a vector to itself. Okay, these kind of vectors goes to 0. So n acts on it trivially. Right? Yeah. Okay, so it's easy to see. So, if I view V as a representation of P, okay, just by restriction, and quotienting out Vn, so n acts trivially, then I get a representation of M. Okay. So maybe I should say this first. Okay, view this as a P representation. but n x trivially. So I get a representation of n. That means Vn is a representation of n. Okay, and remember M is a reductive group. Okay, so we get a representation from my larger group G to a smaller reductive group M, and this is the so-called Soochow module. Okay. Associated to or the Soochow module of pi v associated to P, okay, or N, okay. We use N, but N is coming from P, okay. So this is the Soochow module. Okay, a simple construction. But because we are modeling our large subspace, so we have well, first of all, we have the following. This is a Frobenius reciprocity. Okay, so we have Hom, pi, and if I do a parabolic induction here. Perhaps I don't write down the iota representation. Okay, so I don't want to write down the that modular character. Okay, so this is isomorphic to so here we have the Soochow module, pi n. And sigma, okay, like this. So it's just parallel to this one, okay? But because here, if I take the Soochow module, instead of the restriction, then the representation basically factors through the action of n. Okay, so you can further. And the good thing of this pi n is that. So here I give this proposition. If this pi v is admissible, then pi n on this pi n it means the representation of this m on Vn is also admissible. And I think I'll give a proof here because actually it involves a technique that will be used quite often in, well, at least in the notes for Casimir. Okay, there's a technique that is often used, and because I think that is really cool, so I'll give the proof here. And I think that would be this will be the only proof for this course. Okay, this proposition. But before that, let me see if you have any question for this construction. Before I move on to the proof, any question? No? Okay. Sorry, I should say one more thing before I move on to the proof. think this idea is quite important. Okay, I give it as an exercise. Okay, actually, two exercises, but this one is important. Okay, so exercise 1. So you check the following. Okay, this V bracket N is equal to the union of all V bracket N0. Okay, what is that? So N0 is a compact open subgroup of N. Okay, and the definition is just the same here, but you replace this N by N0. Now, why I emphasize this exercise? Okay, it's easy to see, but you need to observe the following. Observe. Okay, because now we focus on this N part. Okay, in the N part, and a compact open subgroup of N can be arbitrarily large. Arbitrarily large. Okay, it can be very large, and you can take it as large as you want. For example, you can check that, say in GLQ, a group like this, okay, because I'm taking a subgroup of N, so only this entry has meaning. So I take P to the K of set P, okay, the ideal generated by the kth power of P, where K can be very negative. Remember, I take them, okay, so remember this norm, okay? So this P to the K in the p-adic norm, the power is reversed, okay? Remember this minus sign here. That means if K is negative, this ideal is actually a large ideal. Okay, this is very large. If I take K to be very negative, okay, this is large. Okay, because of this, if K is negative, this is positive. Okay, so the length of this is very large. And you cannot, and I should emphasize, you cannot do it for a group, for a reductive group. Say if you have T, okay, if you have something, if you have a subgroup that contains an element like this, how should I say? I want to say you cannot have this phenomenon for say for a torus. this way, okay? In contrast, the maximal compact subgroup of T, okay, is the following. So you can at most have CP cross and CP cross on the diagonal, okay, in T. T is the diagonal subgroup, so it looks like a QP cross and QP cross. And this is the largest compact subgroup you can have. Okay. CP cross is the circle. Anything outside the circle will generate the whole T. Okay. I let you to think about it. If you are new to the this p-adic analysis, then this could be new to you. Okay. I leave it for you to think about. Okay, any question? So the proof of the proposition. So now here, remember I said if you can take a compact subgroup K, which is small enough, okay, take K to be small enough so that it is good with respect to my given parabolic subgroup P, with respect to P, okay? So the meaning is that, i.e. this K can be decomposed according to this n minus m and n decomposition. Okay, the order doesn't matter. Okay, you can shuffle in the order whatever you like. Okay, so but the point is K can be decomposed into a triple product. Okay, you need to take K to be small enough to achieve this. Okay, in the case if P is not good, you can take a smaller one so that is good. Then I leave you to check another exercise. This one is pretty easy. So you just check. Okay, remember this map, PDK. Perhaps I give these subgroups some shorthand notations. So I usually write it n0 minus. This is m0. This is n0. Okay, just a shorthand notation for these factors. So remember this vector map PK. Okay, that maps okay, PK, if you forget what it is just the average map. So it projects a vector to the K fixed policies. Okay, so in particular, if you take a vector V and PKV is its image, then you let pi k to x on this average, then of course you get this average vector. because here you the averaging. So if you have a pi k, it just absorb into this pi k. This pk. Okay. So it's the same as pk. Okay. It's just the usual averaging technique. Okay. So this exercise is about this pi k. Now, pi k is an operator on the. I restrict to this part, the m0 n0 minus fixed point space. So these two, of course, they're subgroup in K. So what we lack is this one. Okay. And I'm saying that this map is just the same as if you just take average on n, okay, this part. Respect to this space. So it's easy to see. And this implies the following. So if I take the k, the k fixed subspace, and then I take more left. It's just taking this Vn. The Soochow module on this subspace is the same as and taking Soochow module. So what's the point? The point is, well, this product is a, so this is smaller, than okay, it's a subgroup of K. So the fixed point space, this whole space, the space is larger than dk. If I take Soochow module, they becomes the same. Okay, and now by admissibility, this is finite dimensional. This is finite dimensional, so the quotient is also finite dimensional. And of course, so is this. And now to show admissibility, for the Soochow module, the whole Soochow module, okay, not just this one. We have to check Vn. Okay, so this is the Soochow module. I take the fixed point of a compact subgroup. Okay. This is a fixed representation. So I take M0, okay, the compact group of n. I want to check this is finite dimensional. So we want to compare this one with this one. Okay. Okay, so how to compare these two? Okay, let's compare this with this. Okay, compare Vn of M0 and Vk n. Okay, compare these two. Okay, and we want to show this is further dimensional. What can we say about these two? Well, we have M0 is a subgroup of K. Then if you take a fixed point space, you reverse the arrow, okay? So you have Vk lying inside Vm0, okay? And of course, this is the same if you apply the Zhifeng module, okay? So, but this has smaller dimension. That's what I want to say. This is much larger. This is much larger. Okay, without doing any studying. Okay, we know this is much larger than this one. This is finite dimensional. Okay, but okay, much larger a priori. But in fact, I'll show that they are actually equal. Okay, so you have an isomorphism. Then this will imply admissibility. Okay, this is finite dimensional, and so is the right hand side. Okay, so how to do it? Say we take a bracket here. And by smoothness, there exists the compact subgroup. Say there's a compact subgroup, let's see, a compact compact subgroup, but I don't want to take the subgroup in M. I want to take it inside N minus. Okay, so this is N1 minus. Okay, this is a compact subgroup inside N minus, such that V is in here. And because we know this is finite dimensional, so we want to bring N1 minus inside N0 minus. But this side, but this subgroup could be large. This could be large, so we don't know how to put it inside a smaller compact subgroup. Before Zhifeng introduced this trick. So here is the trick given by Zhifeng. So this is related to the second condition for this compact subgroup to be good. So this trick, you take an element in this AM. Okay, so this AM is just A theta. If M is M theta. Okay, remember this notation. It's just a subtorus in T. Roughly speaking, this is the center of M. Okay, this is center of M. Okay, take such element, such that, remember we can control the size of A, such that if you are given an arbitrary large subgroup, you can conjugate it to be small. Okay, this is small. Okay, how small? I want it to be inside N0 minus. Okay, remember I did this trick for you. Okay, if you take A to be in the suitable size, then an element like this goes to an element like this, then by controlling C and D, you can just make this entry to be small. And I want it to be small enough so that it lies inside. Then you get, okay, so we consider this fact. A inverse of V. Okay, so what I do is I let A inverse acting on V, and I project it to the N0 minus fixed point space. So what happened? If you use this, okay, you just you can take out. Let's see. Here it should be A, right? This one should be A. So okay, should be A. Yeah, this should be A. So that if A now goes to this side, I have Pn1 minus of V. But V is fixed by N minus, N1 minus. So that this is just pi A of V. Okay. Remember V is fixed by V is in M1 minus. Okay, so in particular it's fixed by N1 minus. So this is gone. And this is pi A of V. So what does it mean? This means pi A of V is in V and of M0 and N0 minus. Okay. So V in here can be brought to here, and what is this? The previous calculation is just VKM. Okay. We want V to be inside here. This is pi A of V. But pi A, remember, this is an M representation. A is in M. That means V is also in here. So we are done. Okay, we are done. Wow, this proves this claim. This shows this law. Okay. So what I want to say is that this Soochow trick is very useful. It's like something like epsilon delta, right? You want to control your A so that this small thing goes to this large thing goes to something small. So it's a quite useful trick in harmonic analysis. Okay, so I'll let's see. Let me give one more proposition, and I'll finish this part of the Soochow module. Okay. So the last proposition for Soochow module. Now here I want to compute the contragradient of the Soochow module. Okay. Remember this is the smooth dual. Okay. Remember pi tilde is the smooth dual of pi. What is the smooth dual of the Soochow module? This is isomorphic to, well, you expect you can do some exchange with the smooth dual and the Soochow module operation. Okay. So you expect you can take smooth dual first and take the Soochow module. It's almost correct, but here you have to do the Soochow module on the opposite direction. So this is true. Okay, so I don't have time to go through the proof. And now I have about 15 minutes, a bit more than 15 minutes. So I will give one example of admissible representation. So this will be the first example of irreducible admissible representation for a reductive group. Okay. So before that, any question about Soochow modules? Okay, maybe I have scared you. So the point is this trick is very useful if you are interested in harmonic analysis for reductive groups. Okay, so here is an example. Okay, so perhaps I give you the name of this representation. So it's called Steinberg representation. Okay, the construction is very easy. So, okay, let me. Okay, so first I define this. Okay, take for any parabolic subgroup. Maybe I should emphasize it's the standard. parabolic subgroup. Okay, P. Okay, so in particular, I take those which are upper triangular. Okay, the standard ones. Then is IP to be just the induced representation from P to G of the trivial representation of P. Okay, this 1P is usually people fold it. Okay, so this is the this 1P is a trivial one-dimensional representation. Okay, of P. It's just a trivial character. And I just induce it to G. Okay. Or you can think about it as a parabolic induction. Okay. It's trivial on M, and it's extended trivially to N, and I take induction. But here I lack the twisted character. It's a modular character. Okay, so if you want, you can write it in this way. Okay. So this is IP. If you don't like this notation, just think about it as this easier one. Okay, inducing the trivial character. Then so remember, an induced representation contains some functions of the larger group G that goes to a certain representation space, satisfying some conditions. And you use those conditions to check, in fact, you can just check all these IP sits inside IP, okay, the minimum one. Or we call it the Borel subgroup. Okay, so this is the just the upper triangular matrix subgroup. Okay. So it's just lying inside, but this is just induced from B to G. Okay, because B is the minimal one. If I induce from the minimal parabolic subgroup, then it contains anything here. Okay, any such parabolic subgroup contains B. Okay. Then what I can do is, so B is the largest. IB is the largest. I mod out all the IP where P are standard parabolic subgroups of G. Okay, P standard parabolic, and P is not equal to B. Okay, I want to mod out everything. Okay, so mod out these, and this I give it a name. The Steiner representation of G. Okay. For example, if you look at GL2, then this is pretty easy. Okay. So this Steiner is just induced from the upper triangular subgroup, but we don't have many choices for parabolic subgroups, right? For GL2, it's just either the minimal one or the whole group. So it's just the induced representation from B modulo the one induced from G to G, so it's just itself. But this is a very large representation. Okay, this 1G is just one-dimensional, it's a trivial character. But this representation has, well, what is its dimension? Is the index of G over B, right? But for p-adic group, this is infinite quotient, okay? G mod B. So this has infinite dimension. Okay. It's like G, the index of G mod B minus 1, but G mod B is infinite. Okay, so you may think this representation may be too large. It contains many sub-representations, but okay, I write it yes, this time of representation is large, but it is irreducible. It contains no sub-representations. I think I don't have time to give you the proof. No, I won't give you the proof, but in fact, I don't even have time to talk about the idea to prove this. What if I give you another fact? Okay, so this is irreducible, and another property for Steinberg representation is that it is square integrable modulo center. Okay, and for the remaining time, I'll explain what this means. Square integrable mod center. So this is the first example of infinite dimensional irreducible representation. Okay, we only saw the one-dimensional representation of the general linear group. Remember, I gave you this character. Okay, I don't write it down. Okay, so the one-dimensional representation that factors through determinant. So this is the first example of an infinite dimensional representation that is irreducible. So, so I hope you have a feeling of how these representations look like. Okay, so it's usually very large. And what is this idea of a square integrable modulo center? So it has something to do with matrix coefficient that Chung Pang Mok mentioned about this a little. Okay, so matrix coefficient. So I just go through it quickly. Okay, you know, some of you should already know what it is. Okay, so the matrix coefficient of pi. Okay, let me just at least write down the full name here for once. Coefficient. Okay. So the matrix coefficient of a representation associated to two vectors, one in V, another in the smooth dual. So it's a function on G, okay, given by given by, so in notation it is C, V, and D tilde. These two vectors input a group element. It goes to, okay, so this, you know this bracket notation, okay, for V and D tilde. Okay. If you don't know this, well, this is basically just the value of this linear functional on pi g dot v. Okay, the same thing. But sometimes people like to write it in this way, okay, in the bracket notation for v and v tilde. Okay, but this is just nothing but the function value. And then okay, suppose that, okay, I don't want to go to general situation, so suppose that pi is irreducible. Okay, then you can check if you restrict pi to the center of G. Okay, so this set is the center of G. That means everything inside, okay, is a subgroup in G, and it consists of all elements that commutes with all elements in G. Okay, just the usual definition you learn in group theory. And if pi is irreducible, then you restrict pi to set is equal to a character times the identity operator on B. Okay. Maybe I write it in this way. So if you input an element in the center, then its value is given by a fixed character. Okay? For certain character, this omega from set to, so it's a character. That means it's one-dimensional. Okay, so if you learn something about representation theory, so this is just the Sher lemma. Okay, so this is the p-adic version of Sher lemma. Any irreducible representation has a central character. Okay. This lemma also happens for finite group theory. Okay, so you can check. Now I suppose this is a unitary character. Suppose that omega is unitary. Okay, unitary, as I mentioned, it means the image. Okay, I write it this way. The image of set by omega, everything has length 1. Okay. That means the image of omega is in the unit circle S1 of C cross. Okay? It's on the unit circle. So it's a unitary character. And with this assumption, we call an irreducible smooth representation pi v of G, square integrable mod center. Okay. A long definition, a long name. If for vectors v in v, v tilde in v tilde, this new dual, this integral, okay, of the absolute value of the function is matrix coefficient. Squared. Okay. Modulo, here on G mod Z, I take dg dz. Okay. Z is reductive, okay, so there's a half measure, and I just take a quotient measure on the quotient space. So you can see from the name, square integrable means this is finite. Okay. So it's just like the L2 function theory for say if you learn functional analysis. Okay. So this is the definition. Perhaps I give you one exercise. Perhaps you already done something similar in finite group theory. Okay, so exercise, if pi is irreducible. Well, actually I assume that this, okay, is irreducible. Then we can replace this word for by for some in the definition. Okay, just check one pair of vectors v and v tilde is enough to claim this representation is square integrable mod center. Okay. So again, using irreducibility is just sort of a standard exercise in representation theory. Okay, so this is the definition. And what I want to claim is Steinberg representation is irreducible and square integrable mod center. So I'll see, maybe tomorrow I'll at least give the ideas of how to prove the first proposition. Okay. Maybe I have time to go through the second, but maybe because I also want to talk about supercuspidal representations, so I'll check. Okay. So that's all for today.